So, hello everyone. I'm Humphries. I'm a software engineer and KDP associate working alongside Leonardo and the University of York, and I'm here today to show you our integrated knowledge-centric engineering approach. And this is an approach for maintaining both agility and rigor in large-scale aerospace projects. So today what I'm going to cover is first the challenge we're facing and why we're actually doing what we're doing, then an introduction into integrated knowledge-centric engineering, or IKC for short, an overview of how IKC works, and then a practical example showing IKC in practice using OpenSea's home security system example. Home security system OML tutorial is a scenario for that. Then finally, I'll finish off by talking about our next steps and what we plan on doing to progress this further, as well as answering any questions that anyone has. I'd like I'd like to ask for people if they've got questions to ask them towards at the end of the presentation, and I'll answer them there. Right. So first, the challenges we're facing. So we have a once in a generation sixth generation aircraft project across multiple different nations with dozens of suppliers and tens of thousands of engineers. It's expected once it's all over to last over 4 years and cost over $1 trillion. So one of the key requirements of this project is that we need to have a 24-hour development and release cycle for new software features, whilst maintaining the current certification standards that are expected for a project like this. So with this in mind, we're going to ask ourselves, how are we going to achieve this on a project of this scale and complexity? So to do this, we have a vision of creating a digital thread between the data from various different sources and artifacts in the project in a way that's independent of any of the tools used for the data or the formats that the data was initially created in. So to do this, we need to have links between the various different domains and disciplines of the project through each stage of the life cycle of the project and through each level of the supply chain for the project. Doing this will allow us to create a traceable narrative across the entire life cycle of the aircraft, making use of robust version control and change management systems to show a timeline of decision making within it. So at what point specific decisions were made for that project. So with this in mind, there is one key trap we need to try to avoid, and that is the temptation to control everything at the top level downwards. So using a top-down approach. We want to try to avoid this because a project of this complexity is not really viable to manage everything at the top level downwards. This creates a risk where engineers at the lower level engineers within the various different teams might try to bypass processes put in place if it comes from the top downwards, which could potentially cause more harm than good. So in an attempt to mitigate the risk of this happening, we plan on taking a more federated approach, meaning that the individual teams will have more control over the processes they have in place. This means if there's any issues with the processes that teams have, they can modify and tailor those processes instead of trying to outright bypass them. This allows our approach to be more adaptive and flexible. So now going through the overall the challenge we're facing and what we're doing. Next is introduction into IKC, integrated knowledge-centric engineering. So what is integrated knowledge-centric engineering? So it is a framework that's described by a set of principles for designing a modern engineering enterprise. Some key points as follows. First, there's a unified and consistent management and integration approach for the various different data and knowledge within the system across the 3 dimensions described above. So the domain disciplines, the stages of the life cycle, and the levels of the supply chain. Top of that, there's also tools for the integration and governance of the data to ensure that the right data is available to people within the project when they need to create domain-specific decisions. This will be done at the operational level using a continuous design and integration process. And finally, we need to be able to have an approach that will facilitate rapid and reliable responses to changes in requirements or design, allowing for us to ensure that the quality of the product is improved and its competitiveness is improved as well. So how do we plan on doing this in practice? So to do this, we plan on having the data. The data is planned to be federated, belonging to the specific domains that it's created. And these are representing system functions according to the system work breakdown structures for the project. Top of that, the various bits of data and knowledge within the project will be contained in what we call information artifacts. The teams that create those information artifacts providing metadata, which allows them to connect to the wider data within the shared system knowledge repository. And next, if a team wants to be able to see what data is available, we plan on having a self-serve portal at the organizational level, which will allow for teams to discover and access data that is available at the organizational level. And finally, for the data governance, we plan on doing that at the stage where the data is created and produced. So what this does, it essentially means that our IKC approach represents a new way of doing the traditional systems engineering and project management processes, parts from the more rigid human-dependent processes to a more machine-interpretable and dynamic system. To do this, we plan on leveraging formal knowledge representations such as knowledge graphs and standardized document exchange formats such as IF. And for the collaboration between teams, plan on using a publish and subscribe network so that where they can access information and the version control and change management will be automated using that. So essentially what this does is it changes the engineering process from an assembly line approach to a more federated publish and subscribe network style. So it's a change of the paradigm of the engineering process. And the key parts of this would be as follows. So first you'd have the publishers. These are the teams and people that are creating data and publishing it up to the shared knowledge repository for other participants to use. You know, your subscribers, they are the participants that will take that data and do whatever they need to do with the data. And then the shared channel, which is your common area where the publishing and subscribing activities take place. So now we've gone through that. Some of the key advantages this gives us is that this approach will be inherently agile with the data within the project being organized by logical precedence, being self-organizing, while also being at a very high level of granularity. On top of this, the data stored within the project it will be stored in a common format and exchanged with a central discovery service. The advantages of this will be that for any tool that is compatible with our IKC approach, should be able to should have interoperability with any other tool that's also compatible. And also will have reusability of the various bits of know-how, components, and assets within the project by using the essential service. On top of that, for handling the dependency management and compatibility within the project, make use of strict version control and enforcing immutable entities, so when data is updated in the project, you keep the original version. And finally, another advantage is the improved automation within the projects that use this. And this is since processes such as these security and certification testing can start as soon as a change is made within the project, instead of needing to go through some more manual processes. This essentially means that testing can start in early stages of the product lifecycle, essentially left shifting the testing stage. So even though we have all these advantages, there are still some significant drawbacks and risks that we need to try to figure out. So the first is there's difficulty in moving away from existing processes. What we mean by that is that a lot of engineers within Leonardo are very set in their ways on the current processes they use. It's going to be a challenge in trying to get them to change from the current tools they use. On top of that, there's also there's a large amount of existing legacy data. I put legacy in quotes because it's still in active use. So we need to try to figure out how we actually handle importing that data into our new style. And next, other disadvantage is that if you want to add a new tool to the IKC approach we're using, it will require an adapter to take the data from that tool and transform it into the common exchange format. Finally, there's a lot of challenges in ensuring that we implement this correctly. We still need to figure out. Still finding new challenges as we go. So now I've gone through an introduction to IKC and how it works. Next, I wanted to show how we are implementing it how we're actually using it in practice. So for the scenario, probably fairly familiar with this, we're using the home security system example from the OML tutorial on Federation, which consists of 4 key actors. So the secure systems, the OEM systems integrator, smart sensors, safe alarms, and supreme monitors. Those 3 actors design the sensor components, alarm components, and monitor components, respectively. So for anyone who isn't familiar with this, I'll give a brief overview of the scenario. So first you have secure systems that would design these home security systems architecture at an abstract level, making use of a specific methodology. That would then get passed to the three component actors who would then implement a design of their component that conforms to that abstract architecture. And after that, they would then be sent back to secure systems who would integrate those components together into a fully integrated and realized home security system architecture. So how do we use this in IKC? So the dependencies between the different parts of the scenario we're using to represent our federation strategy. And by doing this, we would have 6 key what we call workspaces. The first workspace being a methodology workspace. This is where we would find the higher level systems modeling methodology that's used in the example. And this for us would typically be done at the enterprise level and then be reused across multiple various projects and across different workspaces that want to collaborate together. And next we'd have the home security system architecture workspace. This is the workspace where the abstract home security system architecture is designed, identifying its main components and the main characteristics, etc. And then we have 3 component workspaces. So the alarm component workspace, the sensor component workspace, and the monitor component workspace. And these 3 workspaces will take that abstract architecture and realize the component in a way that conforms to it. It's like the scenario in the original OpenSeason. Then finally, we have the home security system integration workspace, which takes the 3 components, brings them back together, integrates them together, and then performs the various different tests that are required to ensure everything is working as expected. So what is a workspace in the context of IKCE? So I'll give you an example of what it would look like for the methodology. So an IKC workspace is essentially a logical separation of the various different tools of data that are being used. So this diagram shows an example from the methodology with on the left-hand side being the various different actors in a workspace, or the team members working on the methodology in this case. They would then use the Rosetta IDE because the methodology is an OML vocabulary. And once they've done whatever development they need to do, they would then go to a transformation layer, which is how OML works currently, which would take the OML vocabulary, transform into RDF into our knowledge graph. And then once it's in that knowledge graph RDF form, we would then have a pipeline that would publish the data in that knowledge graph into a package that can then be subscribed to by other workspaces. So what does it look like when we actually create this? So for creating a workspace, we've started to work on a workspace management UI, which handles the creation and modification of workspaces in IKCE. With this page showing the current homepage we have, but on the left a list of the current active and available workspaces, and the right showing the various attributes for the workspace that's selected. So to create a new workspace, first we click the new button on the top left, which would take us to the creation page. And this page at the minute is actually a form that you would fill in with the various different fields for the workspace, which are in the following order. So first, we have the name of the workspace, and this would be what would be the namespace for the data being developed within that workspace users. Next, we have the template for the workspace, and this is what template is used, what template this workspace will be generated off of. So in this case, the methodology template. Then we have the tools, and these are what tools are required for this workspace, which in this case is Rosetta, followed by dependencies. So what packages will this workspace subscribe to do what they need to do? In this case, it's left blank because the methodology workspace is the top level workspace and has no dependencies currently. And finally, there's the members, and these are who has access to this workspace. So once all these fields have been filled in, you then create workspace button, which would go into the background and create all the different parts of the workspace and take you to the following page. So this page shows an overview of the newly created workspace, with on the top having the name of the workspace, then the right-hand side having a button that you can launch a development environment for the workspace. So once you create the workspace, if you click the open new dev env button, it would launch a containerized development environment where you can do whatever changes you need to do and push them up to the Git repo with the methodology as normal. Then on the left, there's a list of the various different data sources for the newly created workspace. So with that in mind, what are these various different data sources? So in the context of the methodology workspace, they're as followed. So first, we have a master resource, which is an ephemeral OML project that represents all the data currently within the context of the current workspace you're in. And we've got the methodology resource, which in our current example we use a GitLab project that contains the methodology data. And this is, for the methodology, it's an OML project for the pretty much exactly how the OML tutorial is. Then on top of that, we have a development environment resource. This is another GitLab project containing the various templates needed to spin up new containerized development environments for doing development on the methodology. And then next, we have the smart documentation resource, which in this example, we're using an Obsidian Vault, much in the same way that Maggot showed in his previous presentation. And then finally, we've got the CI/CD pipelines and package registries. The CI/CD pipelines being the various different workflows needed for a workspace, such as publishing the newly updated packages to the package registry or updating the smart documentation environment once there's been a change in the master resource. With the package registry containing all the published packages for that workspace, ready to be subscribed to by other workspaces. So now I've gone through that. So what the workflow to actually make changes in the workspace would look like. So first you'd create the workspace, which would spin up all your resources. You'd then create an IDE from the containerized development environment, which in this case is Rosetta. You'd hold the content of the methodology resource, do whatever changes you need to do, push it back. That would then send the changes to the master resource, which would then propagate it to the publishing pipeline to publish it into the package registry. So once that's done, next we would need to make the home security system architecture workspace, which would look like this, and this is very similar to the methodology workspace, apart from one key difference. The top right of the diagram, you'll see there's a second package manager, which is containing all the packages that this workspace subscribes to. And how this looks like in practice when creating it. So the main difference when actually creating it is in the creation form, you would add the methodology as a dependency. And what this does is it creates a link between the two workspaces. So on the right-hand side, you've got the methodology workspace, and the left-hand side, the home security system architecture workspace. And how they link is that the home security system architecture workspace send a pull request to the methodology workspace's package registry that would then push the package to the architecture workspace, ready to be used for the development of the abstract architecture. So this would also slightly change the workflow. So the home security system architecture resource where the development's happening would have another input, which is the methodology package. So now that I've gone through how they link together, I wanted to talk a bit about the data we've used for the abstract architecture and the various components. So to show that we can use data in different formats, I've taken the various OML vocabularies for the abstract architecture and the components. I've made a mix of SysML 1.6 and SysML 2 models. And this slide here is showing how the various parts of the abstract architecture system model would map to its respective parts in OML. So on top of that, also had to think of also thought scenarios where you might have a model in a format like SysML2, and you might want to show it in an architectural framework such as base data model or the C4 architectural framework. So for this example, we picked the C4 model because it's simpler than the face data model and easier to show for this. So what is the C4 model? So the C4 model, it's a set of diagrams that show a system at various different levels. First being the system context level. This shows how the entire system fits by the scope of everything. Then there's the container diagrams, and this shows the high-level technical blocks and how they interact. The high-level technical blocks within the system and how they interact with each other. Component level shows the components inside of a container and how they interact with each other. And then finally, the code level, which shows how a component is actually implemented in code. Essentially, what this lets you do is it lets you show parts of the system. At each level lets you show parts of the system at various different levels of granularity and focus. So how have we actually linked the SysML2 model of the abstract architecture to this? So to do that, we have started to make we've made a mapping vocabulary. So what we've got is on the right-hand side, there's a snippet of the various different key concepts of the C4 architecture framework as an OML vocabulary. So for example, the system concept, container concept, component concept, and the code element concept. These are the nodes for the diagrams of the respective levels. On the left, we've got our vocabulary for the abstract architecture, and in the middle, there's this mapping vocabulary, which will take the various parts of the home security system's abstract architecture, map it to parts of the C4 architecture framework. For example, with the security system being a specialization of a C4 system node, sensor being a specialization of container, and I1 and I2 being specializations of the components. And what this lets us do is it essentially lets us go from SysML diagram, map it to the OMA vocabulary, and then using that mapping vocabulary, map it to our smart documentation environment, which we are using. So you've got the various nodes in that C4 diagram on the right. They map to specific parts of the abstract architecture's vocabulary. So we've gone through that, and so going through the same process before, doing whatever development needs to be done on the abstract architecture. Once that package is pushed up, it then send it to the three component workspaces, and this would work in much the same way before. There's component workspaces sending a pull request to the abstract architecture workspace, then the abstract architecture workspace pushing that package down to the component workspaces. So with that, same as how the abstract architecture was, we took for example, the monitor components and the sensor components, made SysML2 versions of them, showing here how that would map that SysML2 model into respective OMA vocabularies. And once you've done that, same process as before, make the various changes you need to do, then it would then propagate through the various different workflows, publish it to the package manager for each workspace, and then we'd subscribe to those three component packages from the home security system integration workspace. Again, using the pull request and push approach, we were using pub sub approach. So let's say for the actual fully integrated home security system that you wanted to make it as an OMA vocabulary, much like how it's done in the tutorial, but then you wanted to visualize it as a SysML 1.6 diagram. Our approach would let you do that. So as you can see on the slide, there's a slide here. It's various different parts of the OMA vocabulary and how it maps to the respective parts of the SysML 1.6 diagram. So once that's been so now that that's there, the next stage would be identical to the tutorial. So you might make an OML description based on the vocabulary, which can then be shown as a diagram. And this is fully from OpenSea's tutorial. So that's our own overview of how we would use IKC in practice. And then before I go into our next steps and the questions, I want to give a summary of what I've covered. So first, we've got the challenge we're facing, which is sixth generation multi-nation aircraft project with requiring a 24-hour development and release cycle for software while maintaining certification, and then the introduction into IKCE and how IKC works at high level, followed by a practical example using the home security system OML tutorial as a scenario. So what do we plan on doing for our next steps? So we want to continue to work on refining and developing the workspace management UI, since there's a lot of things we still have to get done. And in the nearest term is to start looking at the OML diff algorithm and trying to integrate it into the UI itself. On top of that, we want to take the Obsidian Vault and actually put it into a page on that UI, so it's actually embedded inside of the workspace management UI. Then we also want to try to slightly overhaul and fully improve the workspace creation process by having a builder for the workspaces based on the template that's selected, as well as a process for actually building those templates. And finally, there are still some limitations with our publish and subscribe approach. So, for example, in that scenario, ideally we'd want to have had the integration workspace and the actual workspace be the same, because it's the same actor. Docker and approach, it's not viable to do. So, but hey, we could actually. That is the presentation. I've got some, and my colleague, yeah.
Thank you, Lewis. We have time for one question from Nicholas.
So I'm a bit intrigued by this publish subscribe paradigm. It seems like you're basically saying if an ontology A makes cross references to an ontology B, then the workspace where you're working on A needs to subscribe to the workspace that ontology B is coming from.
It would subscribe to the package for ontology.
Right, that where B is from. Are you using this also to verify that, in fact, all cross-references conform to some publish-subscribe relationships?
Not currently used.
But would that make sense? Because in a sense, like if you had, say, ontology A, right, makes cross-references to ontology B and C, but the workspace where you have A only says, I'm subscribing to some package where B comes from, now you have basically a rogue reference or cross-references from A to C that could potentially be, unmanaged, which doesn't seem like be a good thing.
Yeah, not currently, but that would make sense. Yeah, so you can trace back where the dependencies come from.
Yeah, particularly if C is some kind of a managed package somehow, right?
Yeah.
I have another question.
Mm-hmm.
Sure.
In the beginning, you have shown the example of the next generation fighter approach, which is a complex system. What is the limit? What are the limitations of your approach? I think in terms of baseline definition, for instance, if I have an agility approach here, which is then coming to many releases on a day, or so are there any kind of limitations of your approach? Because you have shown this home security example with 4 system elements.
Sorry, could you?
Yeah, I think if you have a complex system, you at a point you have to define a baseline reference. Yeah. So, and if you have this complex system with many contributors, then you will come to the problem that you have many releases at the day or in the week, or I don't know. So, and this could be an limitation maybe for your approach. How do you think? How can you handle this?
So this is an issue with.
Change management.
So that's what it sounds like to me.
We do plan on implementing version and change management. Probably didn't show it the best in the example, but the packages you subscribe to, you would subscribe to a version of the package. So if there's more, if you've got like the package that's baselined and branching over to various versions, you could subscribe to a specific version of that package. We haven't figured out exactly how we're going to fully implement the version and change management, but it is.
Yeah, but if you think about many thousands of releases a day or so, which could be common maybe, then it's very hard to make a change management, I could believe.
Yeah. definitely a challenge.
I'd say one of the things in the context of a federated system of models is, I know you said there wasn't like a pyramidal top-down approach, but
Yeah.
for managing, I am just like imagining the change impact assessment of somebody fiddling with something, if it's aircraft, change something in the 80s, the CNDH system that has tendrils, and going out and asking everybody, is this okay? And we're going to make these changes because then they import a certain version of the model, and now all of a sudden something breaks. Whether you have it or not, it doesn't matter. You know, I'm not trying to ask if that's it, but certainly it's kind of what everyone's asking about is, sounds to me, is change management. And that's not just like a simple thing like a Git type thing, but it's this broad. When you made it very clearly, when you said $1 trillion, that caught my attention very quickly. And to imagine how much of that, just a small amount of that $1 trillion could make a really cool, elegant change management system in my very uninformed opinion. So, because that's a huge deal for a project of that scale, to be successful at long term.
Okay, thanks very much, Lewis. A nice talk. We will be breaking now for lunch.